Welcome to special cases. So if the number beyond the place to which you are rounding is less than 5, then you want to round down. For example, 1.342 rounded to the 10th place. This is the place with the 3. We want to round down because 4 is less than 5. If it's greater than 5, then we round up. So 1.748 rounded to the 100th place. So now we're rounding to the place where the 4 is. That 8 is higher than 5, so we're going to round that 4 up to 5. Note that you only round once. You shouldn't be rounding this 5 up again. If, however, the number beyond the place to which you are rounding is a 5, followed by any non-zero digits, then you round up. So if you have 1.02502 rounded to our 100th place, so that's this place there, we round up because we have a 5 followed by some non-zero digits. We do have a 0 here, but then we have another non-zero digit, that 2. So this is treated as higher than 5, so we're rounding up here. So this is 1.03. Again, look only one place past the place to which you're rounding. So if you have 7.649 rounded to this 10th place, we're rounding down because we're only looking at the 4. We're not looking at the 9. So we don't look past the 4 to the 9 because including the 9 gives us 4.9. 4.9 would still be less than 5. And if you look at this from a significant figures point of view, if we're uncertain of our 6, then we're even more uncertain of our 4, and our 9 is basically meaningless, so we really can't use it at all. Now let's look at rounding a lone 5. A lone 5 is a 5 without any other digits afterwards, or a 5 followed only by zeros. So there are no non-zero digits after the 5. When we're rounding a lone 5, there are two methods we can use. We can either use the simpler round 5 up rule, or we can use the engineer's rule. To use the round 5 up rule, what we do is a lone 5 is always rounded up. That's very simple. To use the engineer's rule, a lone 5 is rounded up half the time and down half the time. This is accomplished by rounding down if the digit before the 5 is even, and rounding up if the digit before the 5 is odd. For example, 17.75 rounds up to 17.8 because the 7 before the 5 is odd. 17.85 rounds down to 17.8 because the digit before the 5 is the 8 is even, so we round down. So, if a lone 5 follows the place to which you are rounding, then you round to the nearest even digit, is essentially what you're doing here. Personally, I prefer the simple round 5 up rule. It's easier, it does introduce some slight rounding errors, but in general, it includes such a small amount of error that you need to have a very large number of calculations for this rounding to matter. And generally for first year chemistry courses, you don't have that involved in calculations. The other possibility is that you don't have very many sig figs, and if that's the case, then you really ought to get better measurements in your data. Now let's look at zeros. So non-zero digits are always significant. We've already talked about that in the last video, but zeros sometimes are significant and sometimes are not significant. So we need to look at zeros a little bit more closely. We have 4 types of zeros. The first type is leading zeros. So these are zeros in front of all of our other digits. Leading zeros are never significant. So these are things like 0.0005. This has 1 sig fig because all 4 of those zeros are leading zeros. They're all before our other digits. We look at our first non-zero digit. Our first non-zero digit is the 5. Any zeros to the left of the 5 are leading zeros. In the next number that we have, 0.35, the 0 is a leading digit. It's a leading 0. So the 3 and the 5 count, so we have 2 sig figs. Now let's look at zeros between other digits. This is our second type. These zeros are always significant. So if we have something like 205, the 0 in there counts, So the 2 counts, the 0 counts, the 5 counts, we have 3 significant figures. If we have 30.006, all 3 of those zeros in there count. So we have 5 significant figures. So it doesn't matter, the 0 doesn't have to be immediately between 2 non-zero digits. There just has to be a non-zero digit to the left and somewhere a non-zero digit to the right. Our third type of 0 is zeros after all other digits and after the decimal point. And these zeros are significant. So if we have 452.30, the 0 in there is significant because it's to the right of all of our non-zero digits, and it's to the right of the decimal point. So that one always counts. So we have 5 sig figs there. Remember that if a 0 after the decimal point is not significant, then we don't write it. If the 0 is significant, then you have to write it. Our last type of 0 is zeros after all other digits and before the decimal point. And these zeros are not significant if there is no decimal point present. So if we have 200 with no decimal point, that has 1 sig fig. In other words, this number is saying 200, give or take 100, which we really mean somewhere between 100 and 300. This is an estimate, basically. On the other hand, 320 has 2 sig figs. We're still not counting that 0 because there's, again, no decimal point. And this number is basically saying 320, give or take 10. So somewhere between 310 and 330. But such zeros are significant if there is a decimal point present. So if we have 200 decimal point, so 200 point, now we have 3 sig figs because now both of those zeros count, because now there's a decimal point present. And this number is 200, give or take 1. Whereas on the last slide we have 200, give or take 100. If we have 320 decimal, we have 3 sig figs, because now that 0 counts, and this number is 320, give or take 1. So our uncertainty in both of these cases is the last digit written. In this case, it's the 0 in the ones place. On the last slide, with no decimal point present, it's the last non-zero digit written, which was the 2 in 200 or the 2 in 320. This rule means that if you need such a 0 to be taken as significant, then you must include a decimal point. So, what if you want to say 200, give or take 10? In other words, how do you have the first 0 in 200 be significant, but that second 0, so you want this 0 to be significant, but you want that next 0 not to be significant? How do you write it in that case? Because you can't put a decimal point after there and have 200 decimal, because that will mean that both of them count. And we can't put the decimal after the first 0 because now you're changing the number from 200 to 20. The only way to make this clear is to use scientific notation. And we write it as 2.0 times 10 to the 2. So scientific notation is the preferred method for clarity with significant figures. And this is because every digit in our coefficient is significant. Whatever digits you write over here, those always count. So when you're looking at scientific notation, any digit that is in the coefficient or the significand, that is a significant digit. This is why it's called a significand. All of those are significant digits, and the placeholder digits are wrapped up in the exponential term. So, why are the zeros in 200 not significant? This is because they're placeholder digits. They simply act to move our 2 away from the ones place into our hundreds place. And if we write 200 in scientific notation, then we write it as 2 times 10 to the 2. And we don't need to include the zeros unless they're significant, as on the last slide. Now let's look at exact numbers. Measurements with absolutely no uncertainty have an infinite number of significant figures, because there is no digit in which we're uncertain. If we know that all of the digits are right, then there's no uncertainty there. So if our number has no uncertainty, then they don't add any uncertainty to our calculations, so we should essentially treat them as having an infinite number of sig figs, or we're ignoring them when it comes to looking at sig figs in our answers. So there are no digits in our numbers, in our exact numbers, about which we are uncertain, and we're just going to ignore our exact numbers when we're trying to figure out how many sig figs to write in our answers. Exact numbers come into play in a few cases. First, in definitions. If we have a definition, like 1 kilometer is defined as 1,000 meters, that's a definition, and there we have the 3-lined equal sign, and definitions are exact. So the 1 in 1 kilometer is exact, the 1,000 in 1,000 meters is exact. So there's no uncertainty in those values. Because we've defined the kilometer, we're defining 1 kilometer as exactly 1,000 meters. So in each of these numbers, we essentially have an infinite number of sig figs. There is no uncertainty there. So we know that 1 kilometer is exactly 1,000 meters long. We have no uncertainty about any of our numbers involved, and both of our 1 and our 1,000 are exact numbers. The number 1, if you just have a 1 or a 1 in a unit, is almost always exact. So if we look at something like 1 kilometer is equal to 0.62 miles, note here that we just have a 2-lined equal sign, not a 3-line. So this is not a definition. The 1 is exact here, but that 0.62 is not exact. There are about 0.62 miles in 1 kilometer. We can do a calculation that shows that this number is not exactly right, that there's a little bit of error in there, and thus there's some uncertainty there. We're uncertain in this last digit. But here in this one place, essentially what this mathematical equation is telling us is exactly 1 kilometer is equal to roughly 0.62 miles. And if we add a digit on there, then we're getting a little bit more precise. And if we add another digit on, then we're getting a little bit more precise, so on. Whole numbers that have been counted are exact. For example, 2 people. I can't have 1.99 people or 2.01 people. Assuming that I've counted correctly, then I have exactly 2 people. 2,000 people, if we've actually counted exactly 2,000 people and not 1,999 or 2,001 people. If we have 8 pencils, these are all exact numbers. And this is because we can't have a fraction of a person or a fraction of a pencil. These are discrete objects. So either someone is a person or they are not a person. No one is half a person. And either an object is a pencil or it's not a pencil, and you can't have 2.3 pencils. Now naturally you can have different sized pencils just as you can have different sized people, but they're all pencils. If you have 2 unused pencil and 1 heavily used pencil, you still just have 3 pencils. You don't have 2.3 pencils. Now naturally the mass involved or the lengths involved, those would be something else, but those you are measuring, you're not counting a mass or counting a length. With counting, you have discrete numbers, and you can't get anywhere in between. Note that an estimate of a large number of discrete objects is not exact. So the population of the US is 315 million people, but there aren't exactly 315 million people, plus or minus 0, in the US. This statement means that the population of the US is 315 million, give or take a few million. We haven't actually counted all 315 million people. It's theoretically possible for us to do this, but we have to keep really, really good track of every time a new child was born and every time somebody dies. Theoretically, if we did that, we could have an exact count of how many people are currently alive in the US, but it's just impractical, so we estimate it instead. And really, 315 million people for most cases is good enough. We don't need any more significant figures than that. That tells us enough about what we want to know. So our 315 million is an estimate, and there's some uncertainty there. So if you've estimated 80 pencils, instead of actually counting out 80, then you may only have one significant figure. But if you have, or maybe 2 significant figures, if that 0 is a guess. But if you've actually counted them, and you have 80 pencils, you have exactly 80 pencils, then there's no uncertainty there. You know that you don't have 79, you know that you don't have 81, and it may be that you've had to count 2 or 3 times, and they've all matched, and then you can assume that you've counted correctly. So, coefficients and subscripts in chemical formulas and equations are exact. So we have the burning of hydrogen. In oxygen, we have 2 hydrogen, 2 H2 plus 1 O2 yields 2 H2O. All of our numbers in this equation are exact, because we're saying exactly 2 molecules of hydrogen gas, and each molecule contains exactly 2 hydrogen atoms, react with exactly 1 molecule of oxygen gas, and each molecule of oxygen gas contains exactly 2 oxygen atoms. Those react to give us exactly 2 molecules of water. Each molecule of water contains exactly 2 hydrogen atoms and exactly 1 oxygen atom. Note that there's not a 1 written there, but anytime we have a chemical equation or a chemical formula, and we don't have a subscript to the bottom right of a letter or an element symbol, that means that we really have a 1 there. Just like in math class, if you have, or in algebra, if you have x plus 7, what we really mean is 1 times x plus 7. So that was special cases for significant figures.